Hello everyone. In this video, I'm going to show you how to implement finite element method for solving 2D scalar field problems using the three-noded triangular element. In this tutorial, like in this video, we looked at the implementation. When we calculate the stiffness matrix directly, that is, without using numerical integration. So, numerical integration plays an important part in finite element method, but before we understand how to use numerical integration for evaluating stiffness matrices, let's have a look at how to solve this problem, that is 2D scalar field problem, using FEM without actually using the numerical integration, just to simplify the process. Okay. So when in 2D problem, that is, we have the solution field u which we need to solve, and mu is the material parameter. For example, it could be the viscosity coefficient, or it could be the coefficient of conduction if we are solving heat transfer problem, and our u becomes temperature, and f is the source term. Okay, so that's the PDE, and for simplicity, we assume that the material parameter mu equal to 1 and also the source term equal to 1. And we are provided with two Dirichlet boundary conditions. On the left hand, we have a specified value of 1, and on the right hand, we have a specified value of 2. So just to give you a bigger picture, we have a 2D domain, okay, in x and y plane, and our domain goes from -1 to +1 in the x direction, and from 0 to 0.2 in the y direction. This is our 1D problem that we used earlier, and we have extended it to 2D. Okay, so that means whatever the nodes we have on the left side, they all take a specified value of 1, and whatever the nodes we have on the right side, they all take the value of 2. Okay, so again, like we have the unitary solution, this is the solution. So the solution only varies in x direction, it doesn't vary in the y direction, but it's okay. This is a simple enough problem, but which is sufficient enough to understand how to solve a 2D problem using the finite element method. Let us solve this using 4 elements. That is, we are dividing the domain, this divided by 0.2 domain, into 4 elements, and here we have 6 nodes. So 1, 2, 3, 4, 5, 6. All the nodes are boundary nodes, but we have the boundary conditions specified only on nodes 1, 4, which take u equal to 1, and nodes 3, 6, which take a value of u equal to 2. Okay, and that means node 2 and 5 are the degrees of freedom at which we need to find the solution. We need to find the solution field u. Okay, and remember, for this problem, the source term is f equal to 1. Now, with this mesh, we can prepare arrays for the nodal coordinates first. Okay, we have 6 nodes, and their x and y coordinates are this. Remember, on the left side, the x coordinate value is -1. On the right side, the x coordinate value is +1. So for node 1, we have -1, 0. For node 2, which is exactly in the middle, x coordinate is 0 and y coordinate is 0. For node 3, the values are 1 and 0. For node 4, -1 and 0.2. For node 5, 0 and 0.2. For node 6, 1 and 0.2. And we prepare another array to store the connectivity information between the elements and the nodes to which the elements are attached. Now, we have more nodes here. Okay, so for each element, we have 3 nodes. Okay, for example, for element 1, we have nodes 1, 2, 5. So, when it comes to finite element method, the direction of the orientation matters a lot. Because for example, if you are calculating the area or normal, okay, so the area may be plus or minus depending upon the orientation, and the normal will flip, the direction of the normal will flip depending upon the orientation of the nodes. So we need to have a consistent orientation for all the elements. So in this tutorial, we use the orientation of counterclockwise. That is, we order the nodes in the counterclockwise. That means for element 1, we have connectivity as 1, 2, and 5. For element 2, then 1, 5, and 4. So in the counterclockwise direction. Similarly, for element 3 and 4. So that array is going to be this. So for each element, we have the node I, node j, node k. Okay, 1, 2, 5, 1, 2, 5, 1, 4, 5, sorry, 1, 5, 4, and for element 3, 2, 3, 6, 2, 3, 6, for element 4, 2, 6, 5, 2, 6, 5. And remember, so they have to be in the counterclockwise direction, but the order doesn't really matter. So instead of 1, 2, 5, we can have 5, 1, 2, or 2, 5, 1. So the order doesn't matter, but the orientation matters. Okay. Uh, Another example is for element 4, instead of 2, 6, 5, we could have 6, 5, 2, or 5, 2, 6. Okay. You can verify this after running the code. Like after we implement the code, you can verify, you can change this array and then see if the code works or not. It should work as long as the orientation is the same. Okay. Now we look at the element stiffness matrix. So the derivation of the element stiffness matrix for 2D problems is a topic on its own. So for this purpose, we will have a brief look at what is the element stiffness matrix, and we use it as it is. So we have a 3-noded element, and the orientation is in the counterclockwise direction, and we know the x and y coordinates of each node. Okay, so since we have 3 nodes, we have 3 basis functions associated with each node. So n1, n2, n3, and we have only 3 nodes. Okay, and in 2 dimensions, we can represent the basis, the approximation up to a maximum of linear variation. That is linear variation in x and linear variation in y. And we always have a constant term. So these are the constants a1, a2, sorry, a0, a1, a2, b0, b1, b2, c0, c1, c2. So these we can find by substituting the coordinates. And once we know the basis functions, we can plot them for visualization. Again here, n1 should be 1 at node 1 and 0 at other nodes. n2 should be 1 at node 2 and 0 at other nodes. Similarly, n3 should be 1 at node 3 and 0 at other nodes. Okay, and once we have the basis functions, we can calculate the derivatives with respect to x and y coordinates, because we need these derivatives of basis functions for calculating the gradients and also the stiffness matrix. So first we can create the gradient field matrix by populating the derivatives of the basis function. So a1, b1, c1, a2, b2, c2. Once we substitute the values of nodal coordinate, that is x1, y1, x2, y2, x3, y3, we can calculate these coefficients a1, b1, c1, a2, b2, c2 in terms of x1, y1, x2, y2, x3, y3, and that is going to be like this. Okay, so here A is the area of the element, and so we can calculate the area of the element in terms of the nodal coordinates. Once we know G, we can calculate the element stiffness matrix. This is the expression for element stiffness matrix. So element stiffness matrix is the integral over the element domain, the domain of the element defined by the 3 nodes. Okay, and here we have mu, the material parameter, and G transpose G. Okay, this is our G. So G transpose G. Okay, dx dy. This is the second like area integral. Now we can notice that g is not a function of x, and it is also not a function of y. So g is a constant matrix. It doesn't depend on x. It also doesn't depend on y. So we can take g transpose g outside the integral, and mu is a constant. So we can also take mu outside the integral. So all we have left is integral 1 dx dy, which is the area of the element. So which simplifies to mu g transpose g ae. That is, once we know the nodal coordinates, we can calculate g and we can calculate area, and then we can finally evaluate the element stiffness matrix for each element. Similarly, we can calculate the element force vector. So for calculating the element force vector, we need the transpose of the matrix of basis functions n1, n2, n3. Okay. And here n1, n2, n3 are dependent on x and y. So the evaluation of this integral is a little bit more difficult. But after evaluating the integral, we get this as the expression for the element force vector. That is F, which is the source term, multiplied by the area of the element divided by 3, and we have 1, 1, 1. That is the total body force, that is F multiplied by AE, is distributed equally to all the three nodes. So 1 by 3, 1 by 3, 1 by 3. Remember, it's very important. This expression is valid only when F is a constant. Okay. If F varies with X and Y, then this is not valid. We need to follow a different approach. I will show it in the next tutorials. Okay. Now, with these expressions for element stiffness matrix and element force vector, we can start coding. But before we do that, let's see how the assembly works. Okay. So in order, like for your reference, I have provided with the element stiffness matrices for all the 4 elements, and since the area of the element is the same for all the 4 elements, the element force matrices would be the same for all the 4 elements. Okay, so this is for you to verify in case you make any mistake. Okay. Now let us look at the element assembly procedure. So we know that we have 6 nodes and each node has 1 degree of freedom. So we have 6 degrees of freedom for this problem in total. That means our matrix, our global stiffness matrix would be of size 6 by 6. Okay. Now if you look at the element 1, so element 1 is attached to nodes 1 to 5. Okay, nodes 1 to 5. That is, after we calculate the element stiffness matrix for element 1, so all these 9 values go into the rows 1 to 5 and columns 1 to 5. That is this. Okay. So rows 1 to 5 and columns 1 to 5. This is the procedure is exactly same as what we have seen for the 1D problem. See, I hope you can understand that the assembly procedure doesn't change irrespective of the problem, whether it is 1D problem, 2D problem, or 3D problem, whether it is a scalar field problem or vector field problem. That is, when we have more degrees of freedom per node, the assembly procedure doesn't change. Okay. Once we identify the array, we can easily assemble the element stiffness matrices into global stiffness matrix by using the same MATLAB code. Okay. And for element 2, similarly, so once we calculate the element stiffness matrix, the values go into rows 154 and columns 154, like this. 154, okay, 154. And similarly for element 3, so rows 236, columns 236, okay, rows 236, columns 236. And for element 4, rows 265, columns 265, okay, 265, 265. Okay, now if you put all of them together, then we have the element matrix entries from different matrix entries from different elements. Okay, like this. So okay, let's go back. If you put all of them together, so this is from element 1, this is from element 2, this is and from element 3, finally from element 4. So for example, if you look at node 2, so that means row 2, column 2, and at the diagonal entry, okay, we have 3. So it is the node 2 is connected to elements 1, 3, 4. So blue, this green and orange. Okay, blue, green and orange. Similarly, node 5 is connected to 1, 2, 4. Okay, so if you look at row 5 and column 5, that is the diagonal value. So this is from element 1, this is from element 2, and this is from element 4. Okay, so now once we assemble the matrix, we follow the same method for applying the boundary conditions. That is, we multiply the column corresponding to the boundary condition, the specified boundary condition, and subtract it from the right hand side. Since we have 4 nodes for which the value is specified, so we need to do this 4 times. 1, 3, 4, and 6. We know that u1 equal to 1, u4 equal to 1, and u3 equal to 2, u6 equal to 2. Once we substitute those values and multiply and then do subsequent addition and subtractions, this is the final effective global force vector. And then we apply the elimination process. We know u1, u3, u4, and u6. So we eliminate rows 1, 3, 4, and 6, columns 1, 3, 4, and 6. And we are left with a 2 by 2 matrix because we have only 2 unknown nodes with the solution where we don't know the solution. So row 2, column 2. So 5.2 minus 5 minus 5, 5.2. Okay, 2 by 2 matrix with unknowns u2 and u5, and we have the force vector as 0.4 and 0.4. And once we solve this, we find the solution at node 2 and node 5 as 2 and 2. Okay. Now, let's implement this in MATLAB. So in order to show you that the implementation part has lot of similarities between different dimensions or different problems. So what I'm going to do is, I'm going to copy the code from the tutorial 1, that is for 1D problem. Okay, so this is the code for 1D problem. Okay, that's okay. So this is the code from 1D problem. Okay, what I'm going to do, I'm going to save this. Okay, save as FEM 2D, yeah, 3 noded example 1. Okay, now we are going to modify this code to implement the FEM, the finite element method, using 3 noded triangle for this problem. Okay, so here we don't need HLXR, mu and f. These are our material. Mu is the material parameter and f is the source term, so it's the same. And here number of elements are 4, and number of nodes is not a function of number of elements, but we know this. So number of nodes is 6, and we don't have HE here. And for node coordinates, we create array of nodal coordinates. This. Okay. So minus 1.0, 0, 0.0, 0.0, then 0.0, 0, 1.0, 0.2, 0, 0.2, 1.0, 0.2. Okay. So these are our node coordinates, and the number of DYF per node is the same, it is 1, and then we can automatically calculate the total DYF. Okay, and then this part remains the same. Okay, this is our global stiffness matrix, this is our global force vector, this is our solution vector, and this is the vector we use to store the specified values. Okay, and we populate the solution specified array appropriately. Okay, for node 1 and 4 we have a specified value of 1. Okay, so we already have 1, copy. Okay, 1 and 4. For nodes 3 and 6 the value is 2. Okay, for 3 and 6 the value is 2. Okay, and the DYF fixed. Now here we know that node 1, node 3, node 4 and node 6 are fixed, are specified. Okay, so here 1, 3, 4, 6, and from this we calculate the DYF that are free, that are unknown, by taking the difference of the sets. And this element node array, we need to prepare this. Okay, so this is our element node array. 1 to 5, 1, 5, 4, 2, 3, 6, 2, 6, 4. Okay, so this is our element node array. The element DYF array is the same as element node array, nothing changes here. Now we are going to loop over all the elements, and from element DYF array we get the degrees of freedom corresponding to each element. We use it for assembly. So this part, these two lines, they don't change. From these two lines we know in which rows and columns we are going to assemble the current element stiffness matrix and force vector. And these last two rows, the last two lines also remain the same. Okay, only this line we need to change. Instead of like crawling this function for 1D element, what we do, we are going to crawl and another function, stiffness and force tria 3 noded. Okay, so remember last time I told you that we can keep the code more or less the same and extend it to different problems and under different dimensions by simply replacing this function for evaluating the stiffness matrix. That's exactly what we did. So I replaced the function for calculating the stiffness and force for 1D two-noded element to the one where we calculate the stiffness and force for three-noded triangular element. Now we pass the required information, and in this we calculate the element stiffness matrix and element force vector by using these expressions. Okay, so we are passing the nodal coordinate information and node numbers. These node numbers tell us what are the nodes: node 1, node 2, node 3. node 1, node 2, node 3 for each element. Remember, the difference is these are the what we call as local numbers. Okay, whereas here we have the global numbers. These are the global node numbers. So when we look at an individual element for stiffness matrix, so here when we say 1, 2, 3, these are our I, J, K. Okay, so once we know the node numbers, we can get the x and y coordinates for the corresponding node. So we have x1, y1, x2, y2, x3, y3, and then use these expressions first to calculate the area, and then we calculate the gradient field matrix. Afterwards, we calculate the stiffness matrix, and then the force vector. Okay, you see that's exactly what I'm doing. Area A, and then G matrix, K local, so mu multiplied by G transpose multiplied by G multiplied by area. Similarly for force, F multiplied by area divided by 3, and then 1, 1, 1. So here, and then once we calculate all the the stiffness matrix for all the element and assemble them into global matrix vector and force global force vector, we apply the boundary condition. Here again you see this loop doesn't change because we know what our fixed DOFs are. That is where we know the solution and the boundaries. So we loop over all those values. We get the corresponding DOF, and from this array we know the specified value. We get the corresponding column vector from the global stiffness matrix, multiply it with the value at the DOF, and subtract it from the global force vector. So this loop doesn't change. So these are the steps that we are applying in the boundary condition. So 1, 2, 3, 4. It doesn't matter how many DOFs are fixed. So this loop takes care of it. And again, as you can see, this is the same code for from 1D to 2D. We haven't changed anything here, and it will remain the same if you implement the FEM for 3D problems or for any other PDE, for elasticity, for Navier-Stokes. Okay, and the solution step. Again, we are extracting the rows and columns corresponding to the free DOFs. That is, we are eliminating others. We only want the rows and columns corresponding to free DOFs. Okay, and then solve it and populate that solution into the solution array. Okay, here these plots are for 1D, so they're not useful for us now. Okay, if you want, you can keep this exact solution expression. Now in order to plot this 2D problem, I'm going to use this command from MATLAB, try self. So here we are using try self to plot the triangulated mesh. And now if I run the code, let's see what happens. Okay, so there is an error, unrecognized function or variable, solution full. We don't have solution full, we have solution. Okay, it's a small error, minor issue. Okay, so this is the solution. Now let's see if this made sense. We have the domain in the x direction from -1 to +1, and in the y direction from 0 to 0.2. And on the left side, we have the solution as 1. Okay, so this z-axis is the solution, is for the solution. It goes from 1 to 2, and the left side, that is at -1, x equal to -1, we have the same value, okay, which is 1. And on the right side, that is x equal to plus 1, we have a solution as 2, right? 2, which is the same for both nodes. Okay, and at the middle nodes, we have the solution as 2 as well. Remember, if you go to our calculation, so u2 and u5 are also equal to 2. If you want, you can verify this using the analytical solution. Okay, if you substitute x equal to 0 for mid nodes, the value of u at x equal to 0 is 2. Okay, so that is why our solution is correct. Okay, see, so extending the FEM code from one problem to another problem is relatively straightforward. Once you follow this process where we use arrays and we use loops to automate the calculation of the element stiffness matrices. Okay, so this is the beauty of finite element method. Now, here, now like I said, so here the orientation is important, but the nodes can be ordered in any order. Nodes can be placed in any order. That is, instead of 1 to 5, we can have 5, 1, 2. Okay, it should work the same. So, for example, if I say 5, 1, 2, it changes nothing. Okay, and another beauty of this finite element method is if we change the coordinates of the nodes. For example, let's move the node 2 slightly towards the right side by 0.2. That is, so node 2, let's place it at 0.2. Okay, so node 2, we have it at 0.2. Now let's run it. Okay, so of course the solution changes. Okay, and this has an effect also on node 5. Okay, but the what I'm trying to convey is that so this same code works if you change the node coordinates. So that is, this code is agnostic to the nodal coordinates, and we can also extend it for finer meshes. So if you want to extend this to finer meshes, what do we need to change? We need to change the number of elements, number of nodes, and this node coordinate array, and this element node connectivity array, right? Okay, let's move them, and also this DOF fits and this boundary condition. Okay, so let's move them here so that we have all the arrays where we need to specify. Okay, let's not, okay, so let's not move them, but let's modify because we need to specify this array as well, right? Okay. So let us say, okay, I'm going to comment this. Let us say you have a function that gives you the mesh for a simple 2D domain. Okay, node coordinates and make node connectivity array. So this is my function. So I have created this function, so which gives me the coordinates and element node connectivity array for a rectangular domain defined by the coordinates of the endpoints. Okay, so I have called gen-trias. Okay, we have the domain from -1, 0 to 1, 0.2, and first let's use the same number of elements that we have, that is 2 elements in x direction and 1 element in y direction. Okay, 2 elements in x direction and 1. So this gives us the node coordinates array and element node connectivity array. Okay, we no longer need this. So let's remove this. So afterwards, we can calculate n element based on the size of the node coordinates. Okay, node coordinates comma 1. Okay, sorry, this is n node, and then n element as the size of the element connectivity array. Okay, so we can also get n node and n number from this. So it's a matter of what we want to do. Okay, so for example, so I'm just showing you the flexibility of coding. Okay, so here we have n node, okay, and n element. Okay, I'm just changing the names to be consistent. Okay, so let we do this, and then we have them readily available without calculating. Okay, so we have the node coordinates, we have element node connectivity, we also know how many nodes are there, and we know how many elements are there. Okay, if we run this, okay, it should work because we are using the same number of elements, so the solution specified array doesn't change. Okay, so what if we change the number of elements to, let's say, 10 in x direction and 4 in y direction? Of course, we have more elements and this is no longer valid, so we need to update this. So how can we update this? So first let's calculate the nodes on the left edge, so which we can find by doing this. That is, I'm checking the x coordinate value and it should be -1. Okay, so solution specified at all these left nodes should be equal to 1, and right nodes by comparing the x coordinate to the to the rightmost edge, which is +1, and then here we update the solution specified. So for all the nodes on the right hand side, sorry, on the right edge, so they take a value of 2, and our fixed DOFs are, okay, so our fixed DOFs are the nodes that are on the left edge and also nodes on the right edge. Okay, in order to avoid any duplicates, so we can find unique values. and then we have free DOFs. Now, so what have we done? We have only changed the arrays before we reached the element loop for calculating the stiffness matrices and force vectors. Okay, that's all we need. This is our solver. So what we have done so far is pre-processing. Okay, now if I run it, let's see if it works. Okay, some issue. Okay, that's fine. Okay, here we can remove that Mr. White. Okay, so if we run it, what is the problem? So the boundary conditions are not effective, so that there is something wrong. Now let's see what are the left side nodes. Okay, left side nodes are fine, as you can see from the mesh. Okay, so we have the mesh correct. Okay, our mesh. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in this direction, 1, 2, 3, 4 in the y direction. Okay, and then on the left side we have 5 nodes. And also on the right side we have 5 nodes. So our problem might be that the DYFs fixed. Okay, DYF fixed is also fine. So then where else we have the problem? We have the problem here in the display BC. Okay, so that's because our array we have as a column array instead of a row array. Okay, so we can easily fix this by doing this. So the issue was the DYF fixed was a column array instead of a row array, because here we are extracting the second entry of the from the size, so we need the number of columns. So after transposing this DYF fixed array, now the code works as expected. Okay, so on the left edge the solution is 1, on the right edge the solution is 2, and there is a maximum value in between. So the beauty again here is we can change the number of elements, let's say 140. Okay, so it works. Now if you want to extend this program to problems of complex domains, all you need to change is the pre-process step, that is here. So you need to change these arrays appropriately depending on the problem. Your solver remains the same. So if you're interested, you can try different problems. Okay, so there is an example here. You can use this. You can use this solution with changes in both x and y to calculate the boundary condition on all the boundary nodes and plot using the same function. Okay, but just one point before we stop. just note that here we are calculating the stiffness matrix directly, okay, without using any numerical integration. This is okay because this is a linear problem and we have boundaries, the source term as a constant value. Okay, I hope you liked it. See you next time. Thank you.